how one would find the derivative if a function is not given in what we call an explicit form, right? So an explicitly defined function is a function that's solved for one variable in terms of another, right? So here's an example of an explicit form: y equals something exclusively in terms of x, all right? Basically, it's the idea that a variable is defined without using the variable in its own definition, just like the English language. You don't want to, if you had a vocabulary word, you wouldn't want to define it while using the word itself in its own definition, right? So here we have x times y equals 1. We could get that in explicit form, but there are some functions where you're either going to be unable to get it in explicit form, or you'll be unwilling to get it in explicit form, right? So, and that really kind of depends on, how you go about doing things, So, if your algebra is up to snuff, like you might not have a problem putting it in explicit form just to do the derivative, right? But if your algebra is a little weak, you might say, well, I don't want to do that, right? So sometimes it's a choice. But there are, I can tell you, there are some situations where you will just not be able to get it in explicit form, right? So we will need to know how to find a derivative of a function that is in implicit form, and that technique is known as implicit differentiation. All right. So what we do is we differentiate both sides of the equation with respect to x. Basically, what that means is leave the function the way it is. Don't try to solve for y. Don't try to solve for x. Just take the derivative of it in its original state. Right. Once you do that, with steps 2, 3, and 4, really all boil down to getting dy dx all by itself. All right. So take the derivative of your entire equation and then solve for dy dx. So there's a little weirdness that's going to kind of emerge here. We're looking at this function. That is a black highlighter, which just looks weird. Blue. We have x squared plus y squared equals 60. It's actually not a function. It's an equation. We could solve it for y in terms of x. We know that that's going to incorporate a radical. It's also going to introduce a plus or minus. Basically, long story short, it's going to make it messy. So what I want to do is I want to use this implicit technique to find the derivative. We'll graph it after. All right. So I'm going to rewrite the function. And then I'm going to take the derivative of each term of the function. All right. So this is the part that's kind of weird, because when you take the derivative of an x term, it's the way it's always been. All right. So 2x, and then that's it for that. All right. We know the derivative of a constant is going to go to 0. The issue is we're going to take the derivative of y squared, but if we follow the process of taking the derivative, in general, glare? Yeah.
It's like hard to see.
Yeah. Yeah, it's the chain there. Yeah, you just got to pull the chain. I think it's front side is. Yeah, there you go. Oh, it's the back side. That. It's a choice more than anything. So, if I take the derivative of y squared as if it were x, then it would just become a 2y. And you'd be asking yourself, rightly so, where's my dy dx? What we're actually going to do is anytime we take the derivative of a y term, we're going to multiply that derivative by dy dx. All right, which is really kind of strange, right? But it shouldn't be. It's just the way that calculus is taught and kind of has to be taught is you learn all the skills first, and then you start learning why things work the way they do, right? So we try to do as much as we can in the reverse, where we try to get into the why a little bit more earlier on. Because a traditional Calc 1 course would be, all right, learn this rule, learn that rule, take a test, learn that rule, take another test. And then in Calc 3, you'll learn why it all works. You know, it's like, okay, well, what if I never get there? You know, so it's kind of frustrating. So here we get into a little bit of the theory a little bit sooner, right? So if I were to tell you that you had a function of y equals x squared, you would say the derivative of x squared is 2x, right? What does the y become?
Y prime.
We have all the different notations that we could use. You could say y prime, you could say dy dx, right? But really what we're doing, and I'm just going to kind of, and this is the weird part, because what we're actually doing is taking the derivative of this entire equation with respect to x, all right? And we're essentially just distributing through that derivative concept. All right, so I'm taking the derivative of this y with respect to x, so that becomes dy dx. All right, then I'm taking the derivative of this with respect to x, so the derivative of x squared with respect to x, which is why we get into that notation. All right, so we kind of looked at it as our bailout. Like you're doing product rule or quotient rule, and you forgot how to take the derivative of a tangent function, so you just write d dx of tangent of x. You're like, okay, well, at least I'll get most of the credit. But you're really actually saying in notation form that you're including the derivative of that tangent function in terms of x. Here I'm saying I'm taking the derivative of the x squared in terms of x. I can't take the derivative of y in terms of x because I don't know what y is. So that just stays as dy dx. If you wanted to, you could put the little square bracket around the dy just to make it consistent, or just the y, to make it consistent with the x squared. But essentially, it's going to boil down to just dy dx. On the right-hand side, I can actually take the derivative of x squared, and that would be 2x. All right? But we don't show any of this. We go right from here to here because you would have destroyed me if I led the entire concept of derivatives by making you do all of this stuff just to multiply power by coefficient and reduce the power by 1. A lot of why do we have to do that? What's the purpose? If I don't include that on a test, will I lose credit? I would have had to answer that string of questions for every single person that I teach. All right? But now it's appropriate to talk about that because theoretically it makes sense because now it's going to justify what's actually happening here. So notation-wise, and it's still something that you would not have to show, but notation-wise, you're taking the derivative of this entire equation. So when I take the derivative of the x squared, Flonase helps. That's all I can say. Like, you just, I mean, there is something to be said for just the can-do mentality. Like, just keep going until it's done. Yeah. Sorry, you dropped your nose on the floor. Oh wow, look at that bad boy.
What?
Yeah.
Oh wait, I need to take a picture of it. Wait, I need to take a picture of it. Ashley, I'll give you a Can I take a picture of it?
For AP environment?
Yeah. Can I take a picture?
All right. I'll just leave it there in case anybody else needs a picture. I felt bad because I had some folks over. Well, actually, we had a little Mandalorian viewing party, and my wife and I put out a nice spread, and we just went to the grocery store. She washed, I swear she washed those red seedless grapes, but right on the edge of the bowl, there was like a little spider. And so, like, I'm not going to be a bad host. So I picked up the spider, killed it, and threw it away and didn't tell anyone. Let them all eat the grapes. Like, I'm not skeeving people out. Like, listen, what you don't know is not going to hurt you. So yes, there is solid chance that there was a nest of spiders at some point in there. but
Inside of the grapes.
like straight out of Indiana Jones, yeah. Temple of Doom. All right, so what we're doing here is taking the derivative of that y squared function, and that's what this is turning into. I need my red marker. Black marker? Yeah, black marker. This piece is turning into that, all right? And then we would have this piece go into 0, which is easy enough. All right, but the thing is, and again, it's continuous, it's on the move. Continuous weirdness is that we have to apply the chain rule here because we still don't know what y is equal to. So if I were to say I have something to the second power, your response to that should be, okay, 2 times that something. Don't go near my backpack. 2 times that something to the first power, right? But then you also have to multiply by the derivative of the something. So now I have to multiply by, here's my something, the y, which is completely unknown, the derivative of this something y with respect to x. All right, so that little extra component there is coming from the act of following the chain rule. And really, you could think of it that way also, where going from this step to this step, I could look at this as 1y to the first power. All right, y is an unknown function of x. All right, now in this context, over here we know exactly what it is. All right, but I could follow the chain rule. 1 times something to the first becomes 1 times that same something to the 0th power times the derivative with respect to x of that something. Square. All right, and so ultimately this boils down to that. All right, so full disclosure, I didn't understand any of this. When I was a student, I had to stay after school for extra help. It was the only time as a math student in high school that I ever had to stay after school for extra help. It did not click immediately. Everybody has their aha moments at different times. You know, and some people, sadly, will never have that aha moment. All right, where it clicks as to why this works the way it does. All right, but what I will tell you is the process to get you through the solution to the problem. Anytime you take the derivative of an x term, you take the derivative the way you always have. Anytime you take a derivative of a y term, slap a dy dx on at the end through multiplication. All right, and if you do that, you'll always get it right. And what you're just doing is you're buying yourself time until you understand why it all works the way it does. All right, because I stayed after for extra help, and I swear to God, can I say God in the class? The teacher, Mr. Duncan, he explained that concept to me 50 different times. Well, or at least from my perspective, 50 different times. I'm pretty sure he said the exact same thing 50 times. And it was like on the 50th time that it clicked. All right, so, I mean, sometimes it's a vocal inflection. So it's dy dx or d this y dx, dy dx. You know, like for whatever reason, there's going to be a moment where it all just starts making sense. Until that happens, just slap a dy dx on every time you take the derivative of a y term. And then once you get there, it's all algebra. Because now I'm just going to subtract the 2x from both sides. So I'm subtracting the 2x from both sides because my goal here is to solve for dy dx. All right. Solve for dy dx. Get dy dx all by itself as if it's its own variable. So divide both sides by 2y, and I'm going to be looking at negative x over y. And that's my derivative. So everything becomes very easy once you get to the point where you have what we call a differential equation. All right, so you have a differential equation, which is just really, I mean, it's a fancy way of saying an equation that has a dy dx in it. All right, once you get your differential equation, solving it for dy dx should not be difficult. All right, so then all the applications of it should not be difficult either. I don't even know.
41.
41? Okay. Because one, I was looking at the wrong schedule and also the wrong period, so that was not going to work out well for me. What is this the equation of, by the way? X squared plus y squared equals 60? Circle with the radius of? Center? At the origin. If it's in the form of x squared plus y squared, normally the function is x minus h squared plus y minus k squared equals r squared. So the h and k values are 0. H and k represent the center, so that puts us at the origin. The radius squared is the right-hand side. So the 16, root it, you get the 4. All right, let's see if I can draw a circle. Totally going to do it freehand. Why does it keep defaulting back to that? I don't know. There we go. Good looking circle right there. All right, it says find all the points where the graph has a horizontal tangent. What do you know about the slope of a horizontal line? 0. So dy dx should be equal to 0. All right, so I have a dy dx.
Wait, Mr. Kent.
Meh.
I don't know how to proceed from that one. So dy, I'm just like understanding a concept here maybe. So dy dx is just like essentially means the rate of change at that given point, which is the slope of the line, like off of the function.
Correct, the
Which
tangent.
is why it's 0 there. Right?
Correct.
Okay.
Exactly.
Yes. For like 2 weeks ago.
Hey, it happens at different times. All right, so I set this equation equal to 0 and solve. And I get x equals 0. So what this tells me is that, without even creating the graph, is that wherever x is equal to 0, I can expect a horizontal tangent. What do we know about the slope of a vertical line?
It's
Undefined. So we're going to make it 1 over 0.
Why is it positive x?
Oh, because you're going to divide 0 by a negative. So cross multiply, get negative x equals 0, then divide 0 by negative 1. So vertical tangents have slopes that are undefined. So I'm going to take my derivative function, which again is dy dx equals negative 1 over x, and set it equal to 1 over 0. Cross multiply, and you get y equals 0. And you can cross-reference that with the graph. It is asking for points, so we'll have to go back and figure out what those are, but that could come from the graph also. But it's telling us that wherever the x values are equal to 0, so on the y-axis, we're looking at a horizontal tangent. Wherever the y values are 0, so on the x-axis, we're looking at vertical tangents. All right? So just looking at the picture, we would have a horizontal tangent here. You could just eyeball it. So here's a horizontal tangent, here's a horizontal tangent. And here's a vertical tangent. And here's a vertical tangent. All right. The coordinates, pretty easy to spot. For the vertical tangents, we're looking at negative 4, 0, positive 4, 0. For the horizontal tangent, 0, negative 4, 0, positive 4. All right. So at 0, comma, plus or minus 4. At plus or minus 4 comma 0.
Is our test on the 8th or the 18th?
The 18th. Yeah. Yeah, one would be horrible. The other is not so bad. Yeah. No, we're gonna practice for like a solid 2 weeks in class. So plenty of opportunity to get this stuff down. However, if you're not paying attention, you'll have no idea how to do this stuff. Because you might say something like, well, log differentiation, I don't need to know about that. Because y equals x squared has a derivative of just 2x. So we're done. Psh, mere child's play. What we're going to do is start off with a very, very easy problem, something that we already know the answer to. We're using a different technique so that we can get this new technique down. All right. So we are going to take the natural log of both sides of the equation. The log natural. So ln of y equals ln of x squared. All right. The reason why we would consider doing this is because, I always have it in mind. It's an old quote from Men in Black 3, which is like a movie that hardly anybody has ever seen. But it's one of my favorite movies. It's like top 10. Honestly, we will watch Men in Black 3 in this course before it's over. Okay, fair enough.
Yeah, I love the Phantom Menace too. Do I sense extra credit?
That's not even the third one.
He said he loves the Phantom Menace. He did that to get a rise out of me. So it's like, there's nobody in their right mind. Like,
Not a single sane person in the world.
no, there's no way.
Anything in that movie except Darth Maul. So
right. Qui-Gon Jinn, Darth Maul, two of the best one-off characters in Star Wars.
Well, if you count the Clone Wars, then it's not a lot.
Well, and also, spoiler, the movie, the most recent one that nobody saw. Because there was a boycott. Anyway, we could use the power rule for logs. All right. So the rationale, just all kidding aside, the rationale behind using a logarithm is so that we could avoid having to use other types of derivative rules. So what we would do here is use the power rule for logs so that we don't have to use the power rule for derivatives. All right, but there's going to be a power rule in there. So that's my Men in Black 3 reference. One quote in the movie is, where there is death, there is always death. All right, so it's like a very morbid comment, but no matter what approach you use or what pathway you go down, you're always going to have to use the same process, but just in a different kind of, different way of thinking. All right, and so that's what's happening here. Yeah, we got to use a power rule, but in a different universe, the log universe, all right, as opposed to the derivative universe. All right, so in the next question, we'll have a quotient. We have a quotient in the problem. We could use quotient rule for derivatives, but we could also use the quotient rule for logs. All right, so quotient rule is going to happen one way or the other. It's just a question of what universe you live in. All right, so we're looking at natural log of y is equal to 2 times the natural log of x. All right, so what we want to do is take the derivative of this with respect to x. So this is a direct tie-in to what we were talking about yesterday. We're going to take the derivative of the natural log of y and then we're going to take the derivative of 2 times the natural log of x. All right, so now all we have to do is, do that. Oh, thank you. There we are. Right-hand side is going to be easy, because that's strictly in terms of x. 2 times 1 over x, so we'll just say 2 over x. But the left-hand side, well, it's still a natural log, so 1 over whatever is contained within the log. All right, let me just undo that real quick, move it a little bit. All right, so we're talking 1 over whatever is contained within the log multiplied by the derivative of whatever is contained within the log with respect to x. So what do I write? dy dx. So you might look at this and say, well, okay, well, that's not 2x. So clearly we did something wrong, but we didn't, because dy dx, if I multiply both sides by y, 2 over x times y, still not equal to 2x, but I do know from earlier on, dang it, that y is equal to x squared. So 2 over x times x squared, which is in fact equal to 2x. All right, so again, why would you ever do it this way? We're not using log differentiation to learn how to find the derivative of y equals x squared. We're using y equals x squared to learn the process of log differentiation, so that when we come across problems where we absolutely have to use this technique, we'll already know how to do it.
What there is like the answer where you would move it along? Test the 1 over y times dy over dx, or the just all the way down to the dy over dx?
No, all the way down.
Wait, which one? I'm sorry.
The very last thing, yeah, 2x.
So you really are just trying to find like whatever y is equal to.
dy dx is equal to.
Okay. So.
All right, so let's tackle a problem where it's a little bit more appropriate to use this technique. All right, I'm going to skip number 2 because even that case you might look at it and say, well, I could still easily do that with chain rule. Let's look at number 3. That's got some teeth to it, right, Hudson? Oh yeah. Yeah, he doesn't even know what I'm talking to. That guy started talking when he was born and never stopped. So take the natural log of y. All right, take the natural log of both sides. Yeah, Wi-Fi is first disconnected and then now it is, in fact, connected. All right, so I think we'll all agree that just looking at this problem here, it's reminiscent of something that you've worked on with exit tickets. It's got some moving parts to it. It would be quotient rule with some chain rule mixed in. All right, so definitely a little bit more complicated in its original form. So let's see if we can make it less complicated. Now, you would not necessarily think that incorporating a log would make something less complicated, but that's actually what's about to happen. So ln of y is equal to the ln. Now, a quotient within a logarithm tells us to split it apart and make it subtraction. All right, so ln of cosine x plus 1 minus ln. I'm going to rewrite, instead of having it as the square root of x squared plus 1, I'm going to write it as to the 1/2, yeah. Well, it will be negative in a second, but because we made it into a subtraction problem, that's accounted for there. All right, we're also going to swing that around to make it a coefficient. All right. Then once we do that, we're going to take the derivative with respect to x of both sides. All right, we can start trimming out the intermediate steps though. All right. In fact, that middle step here, maybe you trim that one out and just jump right to the third step, because if you know it's going to become a coefficient, might as well just make it that in one shot. All right. Also, the left-hand side seems to be most frequently this weird looking line, so let me try to fix that. Yeah, I just made it look worse. The left-hand side is most frequently y equals. So if that's the case, then once we take its derivative, it's just going to be what it was before, 1 over y times dy dx. For each one of these logs, we're going to apply the log rule for derivatives. Right? You may want to put a little extra set of parentheses around the cosine just to kind of remind yourself that that's contained within the log. Maybe you don't need to do that, it's up to you, but some people have kind of confused themselves and thought it was a product. It's not. All right, when you take the log, the derivative of a log is 1 over whatever is contained within the log. Multiplied by the derivative of whatever is contained within the log. So what's the derivative of cosine of x plus 1? Negative sine of x plus 1.
Wait, what rule is that? Is that a
Chain rule for logs. Yep. Minus, we got the 1/2 constant multiple. I don't have to worry about that. The derivative of the natural log of x squared plus 1 would be what? Exactly. If you want to combine the steps, you can make it 2x over x squared plus 1. But either way is fine. All right. So we've successfully differentiated. In our final step, all I would need to do is get dy dx alone, which means I'm multiplying both sides by 1 over y.
Yeah.
I'm sorry, by y, thank you. Which is this whole shebangity bangity boom up here. Right? So I'm going to take that whole expression on the right-hand side and multiply it by my original y. Which just means that I got to write stuff, but the thinking part is all over. So dy dx would be equal to cosine x plus 1 over the square root of x squared plus 1. That whole thing times everything that we wrote here. Now, just for the sake of avoiding some writer's cramp, maybe you do want to clean it up a little bit. Because if I take negative sine of x plus 1 and divide it by cosine of x plus 1, what would I get? I actually get a pretty clean, negative tangent of x plus 1. You could write it the way it is, but if you want to write less stuff, you could just write negative tan x plus 1. That's optional. And then for the other piece, you can consolidate it all into one fraction. So the 2's would cancel. You'd have negative or minus x over x squared plus 1. Again, that's just serving the purpose of writing less things. This one?
Yeah.
We consolidated it with that to make tangent.
Oh, that's what you did.
Yeah.
Oh, sorry.
So I will highlight that. So that became that. But again, didn't have to do that. Just opted to do that just to make it a little bit cleaner. All right. Now number 4, this one is x to the x. This is a different kind of function, so I'll take you through this one also.
Why should only divide those part by the square root of x squared? Why should only divide cosine x as well?
Oh, because I had to multiply everything by y. And so this is me multiplying everything by y. Y times open parentheses everything on the right-hand side. I think she might have.
So you really just like apply the log rules with chain one.
Yeah. So it's there's really nothing new. It's just how we're implementing all this stuff. Yeah. Which is why we're going to spend 2 weeks practicing all this. Because there's a lot.
Harder, yeah.
Yeah, it's a lot of moving parts. So in number 4, the first step, same. So here I have a coefficient that is variable, x and ln of x. What do you think I might want to do on the right-hand side when I take the derivative? Well, it's a product of 2 functions, right? X and ln of x. Well, there's no log in there. It's not a log of 2 things multiplied. It's 2 separate functions multiplied.
X times one. Oh, did you do that rule, the
Product
product rule?
rule.
So for like this step, it's d over dx because you have the y and the ln.
Right. Well, it's d over dx because we're taking the derivative of this with respect to x and also this with respect to x.
But then at the end, it's dy.
Right. Because it comes out in this step here when you take the derivative of this guy here. All right, so on the right-hand side, it's first times the derivative of the second. What's the derivative of natural log of x? 1 over x, plus my second, which is ln of x, times the derivative of the first, which is just a 1, so irrelevant. So this one actually cleans up kind of in a way where you sort of can't help yourself but to simplify at least a little bit. So we're going to multiply both sides by y to get dy dx alone. But the x's here would cancel. I'd have a 1 plus ln of x times the y. So y here is x to the x power. That's what y is defined as. Oh, dang, I can't get out of my own way sometimes. There it is. So x to the x power. So when I multiply both sides by y, I multiply this side by y also. Cancels out on the left, but on this side I'm multiplying by y. But since y is x to the x and I want my answer in terms of x, I can introduce that. Right? This is the problem where, in the previous case you had a choice. Because you might have gotten through number 3 and said, I don't see how that's any easier than the quotient rule. Quotient rule even with chain rule. I'm not doing it that way. For this one, even though the steps are few, this is the only way to do it. There's no other way to do it. Right? So you would not be able to find the derivative of y equals x to the x using product quotient chain rule. If you think you would use the power rule, well, it's not a power function. If you would think that you would use an exponential rule, well, it's not an exponential function. So none of those techniques are going to work.
And that's because the exponent is a variable?
Both the base and the exponent are variables.
So you couldn't do like the derivative being x squared to the x minus 1?
You could not. You could not. That only works for the power function. So x to a constant power.
Okay.
So.
Why is there the plus ln of x on the where like the last red
Product rule. We did first times the derivative of the second plus the second times the derivative of the first.
Got it.
All right.
For the third line on the right side, you just keep the derivative, that's all you do?
Yep. And then the rest is cleaning it up. Yeah. All right. So that's it for me. And talk to myself while I'm doing it if anybody wants to eavesdrop. So you'd have 1 over y dy dx. That's what I do in my spare time if anybody's wondering. It's really not that bad, but it's pretty bad. So it's really ln of y equals ln of 1 minus ln, well, I could do the 1/2 in one shot. Ln of x squared plus 1. So when I take the derivative of the ln of 1, well, it's constant, there's no variable in it, so that's going to 0. So minus 1/2. Then we'd have 1 over x squared plus 1 times 2x. And then we're multiplying everything by y. So dy dx equals all of this stuff here, which you could rewrite as is if you want. Multiplied by whatever y is, and in this case, y is this, which is 1 over the square root of x squared plus 1.